Okay, so I'm happy to have with us today Nir Rosenfeld from the Technion, previously from Harvard, previously from Hebrew, where I was just told that I'm filling his big shoes. So that's a big honor. And both his job in Technion and also as the talk will hint, relate to the sort of intersection between machine learning and the real world, human behavior, etc. So, thank you, Nick.
Hi, thanks for inviting me. Always fun to be here. Actually, I prepared for Hebrew, so that means do a mental change to me. So, yes, hi, everyone. Pleasure to meet you. My name is Neil. I'm from Technion. I used to be here. I did my bachelor's, master's, and PhD here, so fun to be back. And I'll talk about classification under strategic self-selection, and I'll explain what that means as we go along. So I like to start my talks with this slide. This is machine learning. This is the way we taught. This is the way I teach. I got to teach intro to ML at the Technion. The story is about a machine. It gets input, produces output. It's very algorithmic. It's very abstract. It's very neat because you can use the same methodologies, the same theory, the same tools, the same kind of thinking and apply it to all kinds of problems. So for example, when I did my PhD, it was the time where machine learning became very good at these sort of things, figuring out what the object and the image is. And maybe for people like you doing your PhDs now, you get the impression that machine learning is becoming very good at predicting maybe the next sentence in the world and or our translation. And as time goes on, we get the feeling that machine learning can just be applied to every single sort of application, right? It's abstract. Why not? Just copy paste, maybe with a little tweaks to make it work well. But in principle, why not? And this has made a lot of people think that it might be a good idea to apply machine learning to problems where humans are involved. And why not? Can we just plug humans as input, make them abstract x's and y's? Sure. And this idea is used in practice every day, and I think it's a phenomenon we see increasing. For example, in hiring, maybe you don't know this, but hiring firms tend to use machine learning more and more to screen candidates. There may come a time where universities like ours or yours will do the same thing for their students. Banks certainly do this on a very large global scale. Their decision on whether to give loans or what premiums to give are based on statistical criteria and not always in-depth acquaintance with the person like it used to be for my grandfather maybe. And we're even seeing this in the sort of welfare settings where the state or government is making decisions on how to redistribute its resources back to the community based on machine learning predictive algorithms. What could possibly go wrong? Well, we all know that some stuff goes wrong, and it's easy to point out to things that we have a sense of something is off with just taking machines and using them on humans without thinking a lot further. But it turns out to be quite hard to pinpoint exactly what is wrong. And what we do in our lab is try to ask this question, but from a very technical perspective. From a machine learning point of view, as designers of the machine learning algorithm, how should the fact that people behave in response to the fact that there's an algorithm in the world, how should that change the way we think about learning? How does it change learning outcomes? What implications does it have? And what should we do about it? And so I think maybe half of our work follows the following theme. We think of humans as having agency. It's this very basic truism about people. You can characterize them with three things. They know things, they want things, and they do things together, right? They have desires, they're able to do things, and they use their knowledge to take actions to promote their interests. Okay, and this turns out to be quite challenging to handle within the standard machine learning framework, which just deals with abstract x's and y's. And so our main challenge in all the work that we do is actually about modeling. How do you model these three facts into the machine learning objective in a way that makes sense, is on the one hand simple enough so we can handle it, and on the other hand is sufficiently rich to say something about the real world and hopefully be useful outside. Now, to make this work, because humans are a mess, as we all know, we have to make some simplifying assumptions, because after all, this is research. And after long years, which I have tried to sort of avoid this, I find myself doing the following more and more. Instead of thinking about human beings, Homo sapiens, we think about what is known as Homoeconomicus. These are these fictional rational beings that people in economics like to think about, right? They know everything. They're able to do very technical things, and their desires can be quantified by a single number, which is money. So we don't always go to this extreme, but we found it necessary. Machine learning is a very technical field, and for example, psychology, where I grew up, it's very non-technical. You have, on the one hand, these very soft descriptions of human behavior, and on the other hand, you have experiments, but they're very, you flip one bit in the experiment, and you do a t-test, and that's basically it. And for years, we've tried to make this connection, but it was hard. So we make this assumption on people being rational, so we can make things work together, but our overall goal, and maybe 5-10 years from now, is to take away these assumptions bit by bit and make things become more and more realistic. So when I go through the talk, I'm sure at one point each of you is going to say, well, that's not realistic, people don't do that. I agree, but you have to start somewhere. Okay, so, but this is very general, right? The fact that people want things, do things, and know things is very, very general. Let's talk today about a specific application, which is the labor market, or hiring, okay? How do learning algorithms affect the hiring process? So here's how hiring used to be. Candidates used to show up or submit their application. There was a sort of test, maybe an interview, maybe a trial period, maybe a prep course, something that took time or effort or money. And the outcome of this was a signal for the firm whether they should hire the person or not, right? Where does machine learning come in? Machine learning has become useful at adding this pre-processing stage where people are screened. So lots of people submit their applications. Machine learning goes over all of them very quickly and very efficiently and at scale and make these initial filtering decisions of who to pass to the costly.
Now you wouldn't say machine learning, you would say AI.
I try not to. Sure. Right, so it's this cheap, but very efficient and at scale, low resolution filter that's supposed to reduce the cost for the firm because they can't interview everyone. Right? Wonderful idea, why not? It is being used, but there's this very infamous example, maybe you guys know it, about Amazon. Amazon invested huge huge amounts of money and resources and manpower and research to come up with this very sophisticated and supposedly accurate screening algorithm based on machine learning that was supposed to be very good, but it failed catastrophically, and after, I don't remember, like 7 years of research and development, they had to toss it down the drain after 2 weeks of usage. It was a big thing at the time. I mean, this was 6 years ago, so time has passed. And what actually got the project that I'm going to tell you about today going was a phone conversation I had with my friend Moran Koren. He's an economist from Ben Gurion. We tend to think about the same thing similarly, but from different angles. And he was thinking about this one day, and he told me, well, you know, I have this model that actually explains what happens. Big asterisks will go, in the end, I'll talk about what maybe really happens, but at least his explanation for this is the following. He says that he has a result in a very simplistic, stylized economic model with one firm and one applicant, and you know, everyone knows it. Very, very hard assumptions, but still, in that very simple model, he says that higher screening accuracy, that is, learning is better, learning is improved, means the firm is going to hire lower quality applicants. It's actually hurtful for the company to use this screening. Not only is it hurtful, as you get better at screening, you end up worse. I said, no way. This is impossible. And he said, well, I'll prove it to you with 2 Gaussians. Okay? And he drew these 2 Gaussians on the board, and he started to say all these econ terms, and I had no idea what he's talking about. And in my mind, oh, come on. We know the answer to this. You just put data here, you're done, right? Optimal accuracy. And when I said this, he says, no, that's because you're thinking about learning about it. I'm thinking about the person behind the process. And what he says is the following. This does not describe what the algorithms say. This describes what people are saying. People have to make decisions about whether to apply or not. This is completely missing in the way we think about the role of machine learning in the process. We just assume there is a fixed, unknown distribution D from which we sample pairs X, Y, and we trade, and we test. Done. No. what Mohan told me is that this distribution is the product of people deciding to apply or not. There's a huge pool of candidates. You don't get to see all of them. You get to see those that decide to apply. And what is that decision based on? Well, it's based on actually similar things. They have different names. People have beliefs about whether they're fitting for the firm or not. So you can think of this as two distribution of if I'm not qualified, what are my beliefs, and if I am qualified, what are my beliefs? And people have this private signal. They know certain aspects about themselves. They know where they went to school. They know how they feel about doing things, etc., etc. And they use this information to make an informed decision. They decide whether it's worthy for them to apply or not. Okay? And what he says that happens is that you no longer get this midpoint because other factors come into account. So people have certain value for getting the job or not. There are different costs associated with maybe taking the test, maybe taking the job. There's risk involved. People are risk averse. Machine learning are less risk involved. Each person is an individual. Machine play on the entire distribution. Law of large numbers make them not risk averse. There's uncertainty involved. And all these things make this optimal decision point different from what we would do. And here comes the amazing result. One of the sources of information that people have to make this decision is how the screening algorithm works. So if I know something about the tendencies of the particular firm that I'm applying to for how they screen people, maybe they favor people from Jerusalem, maybe they like people who've been abroad, maybe they like people who play jazz, who knows, then that is going to change potentially my decision of whether to apply or not. So the point he made in this model is that once people know something about the classifier and take that into account, as you increase the accuracy of the classifier, what always happens under certain assumptions is that their threshold for decision making is lower. The decision threshold being lower means that more people apply. But look what happens under two Gaussians. Is this clear what happens? Right? If the threshold was minus infinity, everyone would apply. If it was here, no one would apply. If we move this here, then more people by definition apply. But you get more negative people applying than positive. So what happens here is that by being more accurate, by the classifier being more accurate, people put less weight on what they think and more weight on the algorithm. So take this for the extreme. If the classifier was perfect, then people would notice there was no decision to make. You just apply, and whatever the algorithm thinks, then done. Okay, so it's like they're delegating their agency to the algorithm as it improves. And this is a quirky and interesting result. And our next question was.
Why accuracy increases when you take it to left?
That's the result. It's a proof. I won't show it, but that's the result. The result is under this model, as accuracy increases, the threshold decreases.
Yeah, but it's not so that whenever you decrease threshold accuracy, you just decrease.
No, it's the other way around. You control the model. Imagine you get more data. Your accuracy improves. You think you're doing a better job in screening, and maybe you are, but the implication is that more people are going to apply. The people that will eventually end up in your firm, there will be more negative candidates than positive candidates. And if your interview is noisy, then by some probability you'll see these guys, then some probability you'll see these guys, but you'll see more negatives than positive. It's hurtful to the firm. Okay? So this was a very cool result, and we sat down and talked about it. But of course, being from machine learning, there were some things that were very annoying. So for example, accuracy in Moran's model is a number. It's a scalar between 0 and 1. There's no structure. There's no x's, there's no y's, there's no distribution, there's no algorithms, there's no hypothesis class. It's impossible to ask these sort of questions. Just imagine accuracy. 2, there's no population. This is a very simple and stylized model about a single agent, and it was completely unclear what happens when there are multiple. So all these questions made it clear that it's worthwhile to think about the transition from this in the world of abstract economics to what is going to happen in machine learning. Okay, so this is the goal today. The project is about what happens when you actually take a model and train it in this setting where you use it for screening, and then people get tested, etc., etc. And as we progress, the learning setup will become more. Yeah.
Question: can't we still fit it into the language of just online learning? So you're basically saying there's another IRO. So
Yes, time is a very good point. I'll talk about it at the very, very, very end. For now, I intentionally want to stay the offline batch supervised setting where there are 2 times before and after, right? Okay. And if we have time, I'll try to justify why we tend to do this and talk less about that. Okay. Now, what's nice about this project, as some of the other projects that we have to look at, is that it sort of the setup that I'm going to describe to you of classification under subselection. I'll talk about subselection is it's very nicely at the intersection of machine learning and game theory. And what I mean by this is that once we introduce this very simple fact that people need to decide whether to apply or not, and that this depends on the model, then the learning problem changes sufficiently that we need to rethink about all the things that we usually think about when we try to solve machine learning problem. How we do optimization, what behavior tells us about generalization, is it easier to generalize, is it harder to generalize? Should we think again about how we model loss functions? Are old proxies still good under behavior, or do they become completely obsolete? How do we regularize? What happens to robustness, etc.? But on the other hand, it allows us to ask these new questions that just don't exist in the abstract XY domain, which come from game theory. We need to talk about the incentives of the firm versus the candidates. We need to talk about the role of information. So, for example, the job market is a classic example where the firm has typically more information than the candidates, and we can use it for. Never mind. Okay. And all these questions that come from economics are now part of the learning question. And one of our hidden goals is to make it so that you can't not ask these questions, right? We want to see a world in which when people use machine learning for these sort of problems in the human domain, they cannot escape talking about these things. Just like you can't imagine a paper about machine learning that doesn't talk about optimization. Okay, but we'll see. So after that long introduction, here's the outline. It's very standard. We'll talk about the setup, and then we'll do some very basic analysis about how things work. We'll talk about how to learn and what happens when we learn. I'll show you some very simple experiments, and I'll conclude with a summary. Now, this is a very standard outline because I'm going to talk about a single project. Who was here last time I visited? Maybe 3. No one. Okay. So it felt like it was this. No, it was 3 years ago, and what I did 3 years ago was give this very, very high-level talk, I think maybe about 9 or 10 different projects. Just, okay. This time, I want to dive into the details of one single project. But I'm going to talk less about results. What I'm going to talk about mostly is modeling considerations, because I think this will be most useful for you. Being in Moshe's shoes in the previous lifetime, I try to think what will be most helpful for people coming to the seminar, and I try to think what I liked about talks at that time, and I think the talks that gave insight about the research, the process behind the paper were the most interesting, so I'll try to do that. I'll talk about the compromises we had to make and the sacrifices and what we got from that, and how those trade off. But I'd still like you to think about the big picture when we talk about details of how to think about these questions of what happens when you take machine learning and plug it into the real world with actual humans that do stuff. Okay, problem set. So here's your typical supervised offline machine learning setup. We have x's and y's. X's, think of them as candidate features. Y is binary, whether a candidate is qualified or not. I'm going to make this little structural assumption that will pop up later. We're going to assume that a subset of the features are discrete, categorical view. Okay, it's not. It is important in some sense. It's not important in others. When I get back to this, just keep this in mind. Okay, we're going to get a sample set, sample IID from some unknown fixed distribution, and our goal is to learn a screening classifier that's going to predict whether people are qualified or not based on their features. Great. So here's your standard learning objective. From hypothesis class F, we're going to find a good lowercase f that minimizes the expected 0, 1. Great. Okay. Now, if you remember what I said about people, we need to think about 3 things: what they know, what they want, and what they do. Let's start with what they do. So one thing that people tend to do, and this is actually the action that's maybe 99% of the literature, the strategic learning literature talks about, is the following action. People have features X, and based on their knowledge of the classifier, they modify their feature in a way that does something that they want. So for example, think about taking your CV and editing it in a way that you think increases your likelihood of passing screening. Or maybe even if you're smarter and willing to invest more, maybe you're going to volunteer somewhere or start taking piano lessons because you think that's helpful for the class. Yeah?
A very naive question. You assume that we know age.
Yes.
So to what extent it's true?
Okay. So I talked about this last time, but this will come up again when we talk about information, so don't forget the question. But yes, the predominant assumption is in this literature is that the classifier is that people know age, and there's a big question of whether that's relevant or even if it's useful. But we can talk about that. Okay, but I'm yes.
Sorry,
Yeah.
just to clarify, is this like saying people apply, or is this
Ah, okay.
it's a larger set of candidate features that they choose?
So this setup talks about people gaming the system. They make changes to X without changing Y, but then you can also talk about causal effects of how changing X also maybe changes Y, and then it's not necessarily gaming. Okay, these are great questions. The thing is, I'm not going to talk about this. Okay, so what I wanted to say is that and this literature is fixated on people doing only one sort of thing, which is changing their features in whatever way you think possible. And so we tried for a long time very hard to think about what other stuff do people do that's interesting and we can think about. So this is called strategic classification. If you're curious about this, it's a very fun literature. We have lots of papers about it. We've been thinking about it carefully for the past 4 or 5 years. But today I'm going to talk about a different kind of action. Like we said before, this is the action of participating. People make a decision of whether to apply or not. How does the objective look like now? So if before the classifier affected features, now features are unchanged. The objective is the same. What changes is the distribution. So while we assume the training data comes from the clean distribution P, with every choice of F, your goal is to generalize well to the induced distribution. What is the induced distribution? It's the distribution of people that apply. So anyone who does not apply gets kicked out. And you look at everyone that applied and normalize the distribution. Okay. This is a new task which we call strategic classification and strategic self-selection. And you can think about it in this way. For now, this is fun again, but imagine people as being sorted into groups. And if this is the original distribution, having 4 groups, then maybe under one model you get 2 groups that apply, but 2 that don't. And maybe under a different model you get 2 different groups that apply. Maybe under some model everyone applies. Maybe under some model only 1 group applies. Okay? So when you choose a classifier, it's not that you want it to be good on P. You want it to be good on PF, the distribution that the classifier induces. Which is very neat from a learning perspective because it makes the learning problem tricky, right? It's this 2-stage thing. Learn in a way that induces a distribution on which your classifier is good on. Okay, so we have the objective. Let's talk about how people make these decisions. How do people decide whether to apply or not? Now, denoted by A star, the optimal decision, which is like saying people are rational, this is how they decide. Okay? Rational agents make decisions as long as they're worthwhile. Okay? What does worthwhile mean in an economic sense? It means that they're going to apply only if they get the value they gain from applying is larger than the cost they're going to incur with applying. Now, what are values and what are costs in our problem? Imagine candidates getting maybe a value of 1 from getting the job and 0 from not getting the job. And the remodel cost is coming from the test. So sending your CV is for free, but if you pass screening and you get invited to a 3-day interview for which you need to prepare for 2 months, then that's costly. Okay? Let's call this difference value minus cost utility and rephrase the question of when is utility greater than 0 for these candidates? And for these, we need to think about the setup more carefully. So let's start out with the fact that people applied. At some point later, they're going to be tested. Okay? Now we're going to make this very simplifying assumption that's going to be useful for us, but maybe will annoy you, and that the test is going to be perfect. So the interview is going to expose with probability 1 whether you're qualified or not. Okay? What happens when it doesn't, we don't really know. Things become very involved, and it's complicated enough without this, but it's a very interesting future question if you'd like to do. Okay. So we also know that the role of the classifier is to screen before testing, and anyone who passes screening is going to go be tested, but if you don't pass screening, then you're out of the game. Okay. Now, what is the utility that people gain? Then we can see that when they pass screening, then if their y is 1, then they're going to get value of 1, but they're also going to pay the cost of being tested. And if they pass screening but their y is 0, then they're not going to gain any value, and they're still going to pay the cost of being tested. This justifies why there's a decision to be made at all. So people need to decide whether they're willing to risk passing screening and paying the cost for nothing, versus will they pass screening and testing and get get higher, meaning they get 1 minus c, so this c is smaller than 1, okay? And the way they're going to make this decision is by considering these outcomes. So if they don't pass screening, they get 0. They pass screening and don't get testing, minus c. Pass screening and testing, 1 minus c. Yes?
Are we assuming 9 has no cost?
Yes, it's free. Okay, so we could write this down compactly as the optimal decision is apply only if you pass screening and if you're qualified. Okay, this is what they need to do. Yes.
If the person knows his why, then there's no dilemma. So
Great. Decision making is interesting when there's uncertainty. Anytime there's no uncertainty, decisions are not decisions. They're just passive things that happen. Okay? The greatness of behavioral economics is taking into account the fact that people make decisions under uncertainty. That's where things become interesting. So, and this becomes again a question of information, which is the second thing we need to consider. What do people know? Yes? Okay. So here's the assumption. They know X because it represents them. But they don't know Y, and they don't know Y hat. Okay? Maybe in some realistic world, you would think of people as knowing something about Y. It's possible, it makes sense. But the cleanest setting, and this is one of the sacrifices we make, we assume people do not know Y and do not know Y. Okay?
So you said you assume they have to know something about the classifier, otherwise it wouldn't affect their. But do we believe they know something about the learning, the relation between X and Y?
It's going to come up now, and it will justify why we make these assumptions, because it's going to be so clean and elegant that you'll have a hard time saying no. Yes?
Why haven't there been these how
Okay. What everyone here is saying is that people can make these decisions because there's uncertainty involved. If there's uncertainty, then there's a distribution over something. And so instead of maximizing utility, they should be thinking about maximizing expected utility, which is exactly what rational agents do under uncertainty. Okay? So what is this expectation over? You need to take an expectation conditioned on X. You need some distribution or belief over the joint relations of Y and Y hat. Okay? Now, one avenue we could have gone in, and it's not a bad one, but we got stuck very quickly, is making maybe parametric assumptions of what these beliefs are. Maybe they're I don't know. We didn't want to go there. Instead, we did the following. We assumed that the firm makes public some very coarse statistics about its hiring process. Okay? What does this mean? So here's a real-world motivation, but in a different application in banks and loan. In banks giving out loans, you know what FICO scores is, like credit scores? Okay, so you can find online credit score calculators. They ask you a series of questions. So how many credit cards do you have? And you click, and then you see the file, and what are they? And maybe 10 or 20 questions. And after that, what you get is not a score, but a range of possible score. And why is there a range? because the questions you've been asked are only a subset of the information that FICO takes when they calculate your actual score. Okay? So think of this as some sort of probabilistic confidence interval around your actual point prediction, which you're not given because you don't know the readings. So as motivation, we wanted to have the same thing. We wanted the firm to publish these statistics about course level information that people have. And this is where the Z that I mentioned before comes in. Okay? So because our problem is classification and not regression, what we imagine the system releasing is these. For every Z, because Z is discrete and you have a countable set of these tables, there's a table describing the joint distribution of Y and Y hat. So this is like asking the firm to say, look at all the people you've ever said. Okay, this is problematic, but just look at all the people there are. Tell us who you classified as 0 and 1. Tell us whether you found out they're qualified or not, and whether they're statistics conditioned on Z. So this is like you coming in and saying, well, I went to this school and studied this subject, and I got this grades, and got that SAT, etc. Then here's the probability of every possible relation. Okay. Now this is not yet realistic. I can't imagine any firm releasing, I don't know, 5, 10, hundreds of these tables. But what we show is that under the assumption that all the beliefs that candidates have come only from these statistics that the firm releases, they don't have any individual information of their own, they're not biased, there's no noise, they don't listen to their friends. When this happens, then the decision rule, the optimal way to apply, is very, very, very simple. You just need to ask whether the precision of the Z that you have is larger than the cost of the test. That's it. Okay. Now, what is precision? Precision is the probability of being qualified, given that you passed screening. And this is very natural criterion for people making a decision, right? They have to say, should I apply? Well, I need to think about, if I pass screening, what is the likelihood of being qualified? Because that's where costs come in, right? If you're not qualified, you pay -1. If you are qualified, you get 1 minus C. And it turns out that our problem, this is the only thing you need to consider, okay? Suddenly, thinking about a firm releasing these precision metrics becomes more reasonable, right? This is maybe a simple analog of confidence interval in the world of classification, okay? So what's nice about this is it's super clean. The only thing a person needs to know whether to apply is, for his particular Z, whether the precision is higher than C. But if you think about this carefully, then, okay, I'll say this soon. Now, what is precision? Just to get the sense of it. So here are two distributions. This is the distribution of Y equals 0, the unqualified and the qualified. The precision is the area of the positives over the joint area. Right? This is the classification rule. This classifies everything here as Y hat equals 1 and Y hat equals 0. And now you see for a different distribution, the only thing I changed is the base rates of each, the zeros and the 1, and precision becomes different. So where is precision higher and where is precision lower? This is a higher precision, right? Because the relative area of this is larger. And you'll see this coming up again. It's not by chance that when the positives have a larger ratio in the population, then the precision becomes higher. Okay? We'll see that again. Okay. There's one annoying artifact which you may not like and we do not like at all. And it's the fact that we get here that everyone having the same Z makes the same decision. Okay? Now remember, Z's are discrete, so you can think of them as partitioning the population into groups. Each assignment to Z is a different group in the population. So what we get is this very group behavior. The entire cohort of Z either applies together or does not. And this is clearly an annoying artifact. The problem is that once you allow these decisions to become individualized, then you either need to think about how do they differ, right? What is the source of variance? Is it noise? Is it coming from what the firm does? Do they have private information? Modeling becomes trickier. 2, once you have individualized decisions, then you need to think about the firm estimating the distribution, right? It's no longer a discrete distribution that you can characterize by tables. You need some parametric form, and Not worth it. So if you bear with me, let's go forward in a world where people make decisions as part of the group. Okay. Great. Let's talk about incentives. We know the firm wants to be accurate. That's the goal of screening. And we saw that people are supposed to care about precision. This is accuracy. This divided by everything. This is precision. This divided by this. Okay? How are they related?
The firm pays a price for the test. What's
Very good question. So, if we were to model the firm's utility, then yes, we would think about the test being also costly for the firm. Then the firm's objective would not have been accuracy; it would have been maximizing utility. This was a point where we've considered again and again and again and again, and concluded with the decision that we should think about a firm seeking to maximize accuracy because it tells a story about what's happening now in the world, not about what should happen. As a rational firm would maximize utility. Just your average firm would hire a bunch of undergrads that completed the course in machine learning and tell them, well, this looks like a nice idea, implement this, do this. And we want to ask what happens when you do this. Is it going to work? Is it going to fail horribly? And if so, okay.
Why the term 6 AQAC and not something with precision and recall and waiting?
We'll get to that. So order 0, maximize accuracy. We'll later talk about a firm that's increasingly smarter. It'll still care about accuracy, but it'll become more and more aware about the fact that people do things, they have agency, and they care about precision. That's definitely going to come. But first, let's try to understand the relations between accuracy and precision. So one benefit of getting the decision rule being dependent only on precision, sorry, this is parentheses, is that precision is a well-known metric in machine learning. Like we can talk about it and understand what we mean. And there's also a very nice characterization about the relation between accuracy, precision, recall, and base rate, and we make use of this in our analysis. Okay, so how do they relate? Here's a very, very basic analysis of the incentive structure of the problem. So first result is that the utility to candidates is monotonically increasing in precision. Okay, now this is clear. Well, no. Having high precision is better than, having precision 1 is better than having precision 0. Why? Because if you have precision 1, then maybe you apply. If you have precision 0, then you never apply. Okay? But there's a stronger sense that they're connected, the utility is monotonically increasing, but only if you hold this guide peaks. So there is a monotonic relation between them, but it's not precise. And this not being precise is important because having more precision is not always better for the candidate. For example, you can think of 2 classifiers, the first having higher precision than the other, but utility for the candidate under the first one is lower. So it's not that globally higher precision is good, it's more nuanced, and we'll try to dive in and understand what exactly candidates want out of precision. It's not just being, okay? And third, there's this nice characterization that shows that sometimes accuracy fully determines what's going to happen, deterministically. Okay? So if accuracy is lower than this term, and we'll talk about it in a second, then this group is not going to apply, no matter what. Okay? If there's some subset of the population, if there's a group which is very difficult to classify, no matter how much the classifier wants to classify them well, then they're doomed. They're not going to apply. The other, there's also the flip side. If accuracy is sufficiently high, if there's a group that's easy to classify, or the classifier cares about, or if it's the majority group and the classifier puts most of the effort on classifying it, then they're going to apply and there's nothing you can do about it. You can't prevent it. Okay? And otherwise, if it's not above or below this or above this, then anything can happen. Decisions are unconstrained, and it says people still have agency. Okay? Now, what's important about these terms is the role that mu, the base rate, right? This is the probability of y equals 1 in this group, and the cost split. So if there's a minus and a max and a 1 over and a minus again, so I'll summarize it for you. If base rate is higher, then it's easier to apply. Okay? We saw this in the graph with precision. If I'm in a group that has more qualified candidates, then it's going to be easier for me to apply. Okay? It's sort of a preference, a global preference for higher base rate groups. On the other hand, as you increase the costs, then it becomes more difficult to apply, and this only makes sense, right? If the costs of the test are very, very, very high, then less people are going to apply. And these two parameters are going to be things we play around with to understand what's going to happen. Okay. Now, as I said before, until when do we have?
11:30.
Oh, no. Okay. Okay. So what we'll do now, once I hope you have a good sense of the problem structure, the setup, let's talk about learning. And I'm going to start with analyzing what happens under naive learning, that is just optimize something for accuracy without even thinking about strategic behavior. Then we'll talk about this idea of what is the minimal thing you would change in learning that takes into account the fact that people behave, which is exactly thinking about precision as you learn or after you learn. And the third thing will be this ideal setting where if a firm knew exactly how people behaved, then how can it learn in a way that anticipates the behavior and maximize? This is the firm being strategic or the learner being strategic. Okay? And for these three different approaches, we'll ask what happens to the firm in terms of accuracy, what happens to the candidates in terms of the utility that they gain, and what happens to the society in terms of who applies and who does not across groups. Okay, so here's naive learning. It optimizes learning for the base distribution, but it gets tested on the strategic induced distribution, right? Because people in the world still do apply. Let's think about a very simple problem, our two Gaussians again, okay? Here's a group, two Gaussians, same base rate. The firm is going to train on this. We know the answer. It's going to apply. What is going to happen? Will outcomes be better once people apply? Will outcomes be worse once people apply? Or will outcomes be the same once people? Now this is a trick question because the answer is anything can happen. Here's three very simple examples of induced distributions where either of these happens, and the only thing we change is the base rate. So if the base rate stays the same, then what happens is that the decision threshold for applying is lower, just like in Moran's result, and people here still apply. So it turned out that nothing changes. You learned in a certain way, you anticipated this sort of behavior, but in the real world, things just happen to work out like nothing happened at all, okay? But it doesn't have to be that way. If we decrease the base rate, then what happens is that learning becomes worse, okay? You imagine seeing everyone, but eventually only one group applies, and that is the group having lower accuracy based on your model trained naively. But if base rate was higher in this other group, then the other, you get the flip effect. That other group that applies is actually easier to classify than you expect. Okay? So the conclusion here is that outcomes are completely arbitrary. There's no way to know beforehand whether your accuracy is going to be better, worse, or exactly as you thought, because it all depends on how people apply, and you haven't thought about that carefully.
So just to make sure you understand, what happens is the better you are on the groups that have a higher chance of being hired, so not only you're better in predicting, you're also increasing their chance of participating and therefore helping yourself. So in a way, what you would really want is to be really good on the groups that have a good chance. So it's like something weird.
Exactly.
Like
if what you care about is accuracy, then yes. And that's going to come up in results. Okay. So that's naive learning, and it's very clear that it's very restricted, and we sort of understand now why. So let's do the next natural step, which is think about the precision of the classifier that we've learned. Now there are ways to optimize for precision, but like I said before, it's not exactly clear what you want out of precision. Okay? Here's an idea that's maybe the most common approach to tuning precision. Train a classifier naively for accuracy, and then vary the decision threshold of the score function right? Tune it from, I don't know, minus infinity to infinity or 0 to 1, depending on what the score function is. And that gives you a range of all possible relations between precision and likelihood, given that this is your score function. And you can plot this on a precision recall curve, and you get it. Okay? Now, it's tempting to think that what happens is that as you increase this threshold, the precision increases, but that's not true. That's actually true for recall. Recall is monotonically increasing. Because precision is conditioned on predictions, it generally increases, but not necessarily, definitely not locally. Precision curves tend to look like these crazy things. The regions, they go up, they go down. It's very hard to do. So what we did here is we found this property, which we call calibrated score function. And we can show that when classifiers have this property, then precision monotonically increases. And it's an if and only if condition. Okay? Intuitively, what this property says is that the score function captures the general direction in which the probability of y equals 1 increases. And this happens globally. Now, it feels like a strong condition, but it's actually weaker. It's implied by standard calibration, which is classifier calibration, probabilistic classifier calibration. So we don't see, I mean, it's hard to imagine this is going to happen in practice, but as I'll show you soon, even if it holds approximately, then we still get basically monotonic behavior and precision. Now, the reason we care about this is that now we can say things that are interesting. For example, when the score function that you've learned is calibrated, meaning that precision is monotone, then an easy corollary is that applications are a step function. Why? Because we know that the optimal decision is apply when precision is greater than costs. And if precision increases in this thing, then there's going to be a point where it crosses the cost, and it turns. So it's either fixed at 0, it's either fixed at 1, or it flips from 0 to 1 at a single point. Okay? Now what's nice about this result is it tells you the following. If you apply semi-strategic learning, that is train naively and then tune precision, and if this condition holds, if you've learned a calibrated score function, then the way applications are going to behave is according to the order in which your score function scores different groups. This score function induces an ordering over groups, and if a group with a lower ordering applies, then any group above it has to apply as well. Okay? So this is good and bad in two ways. It's good in the sense that we understand what's happening, and it's reasonable for applications to behave along the lines of phi. But it's also restrictive in the sense that it's easy to come up with an example where these constraints make it so that this sort of approach is never going to be optimal. Okay? Because the optimal classifier is not, the optimal application structure does not comply with this order. Okay? And what I wanted to show you is this. So this is a simple experiment, again on Gaussians. We have 10 different groups. This is the precision curve, so we increase the threshold, it's a probability threshold from 0 to 1. And what we see is that even though the score function is not calibrated, most curves are mostly monotonic, and what's more important, all applications are step functions. This shows the point where each group applies, and you see this very nice ordering happening. Okay, and what's also interesting is that you see that some groups. I'll talk about this. Okay, I think this is coming first. Okay, so let's talk about what happens when the threshold is 0. Okay, claim when the threshold is the lowest possible, then precision at this point is exactly the base rate. Why? Because precision is the probability of y equals 1 given y hat equals 1. If the threshold is minus infinity, then everyone has y hat equals 1. So you condition on nothing. So just the probability of y equals 1, okay? Which is by definition the base rate. So it means that when you start out, everyone is ordered by their base rate, okay? And what happens is that even if a group has a low base rate, it still has a chance to apply before other groups. This happens if its slope increases quickly. Okay? That is, if very quickly it's either to distinguish which of its members are 0 or 1. Okay? And you see the other way around. You can have groups with very high base rate, but their slope is very low and they apply only at very late stages. You also have some groups that never apply at all, because no matter what you do, the precision is never high enough for them to submit in middle process. Okay? Now, except being nice in terms of have an understanding of what happens, it tells a story. So now imagine a firm. It says, well, you know what? I'm not going to screen anyone at all. What's going to happen? Whoever applies, it means they have sufficiently high base rate. Okay? It's like this game is never played at all. Okay? So a firm that's smart enough to know that it can be happy if these groups apply is just going to say, well, you know what? We're not going to do screening. We're not going to כן, לא משנה, להפלות, discriminate, תודה. We're not going to discriminate against anyone, but they know that discrimination is going on and this is going to come up again. So, okay. Oh, I have to hurry. Wait. Okay, okay, let's talk about strategic learning. Okay, this is the fun part, which I saved for almost last. So in strategic learning, maybe I'll give you in a high level. A strategic learner is going to solve the correct objective in the sense that it's going to have these A's inside the objective. Okay? Due to time constraint, I'll only tell you that the way we solve this is we have this way to make applications differentiable. We have a differentiable proxy. It's not trivial. We need this very strange kind of sigmoid instead of the other one. There are all kinds of other things involved. But it's very nice because you can take gradients through these application decisions, and it turns out very nicely. Okay. Here's the main result in terms of analysis for strategic learning. And this is, I think, our main result in the paper. If you have a learner that's strategic and it can anticipate exactly how people are going to respond, then it has the power to determine exactly which groups apply and which do not. Okay? And the way it does this is by controlling their group thresholds. Okay? A sophisticated learner is going to, just like before, say, well, you guys have a very high threshold for crossing and you have a very low threshold for crossing. And why should it do this? Why should the outcome be only one group is going to apply? Well, that's easy because each of these groups think of it as having, if they were alone in the world, they would have their accuracy. The group of any combination of group, the accuracy of any combination of groups can only be lower. So the best thing the firm can do is select the group which, had it been alone in the world, had the higher accuracy, make sure they apply, and everyone else does not apply. So strategic learning is very, very powerful in the sense that it can fully determine who applies and who does not. And if it wants to maximize accuracy, then only one group in the population is going to apply. Okay? Now what's bad about this result is it can create an appearance of fairness. So here's the firm saying, well, here are my candidates. See, it's very fair. We have the same ratio of oranges, the same ratio of blues. But why did this happen? It happened because the firm made it so that everyone else did not apply. So it shows the group that it was easy to get fairness to work on, and it made everyone else not apply. So it's sort of rolling the responsibility onto the people themselves. It's saying, I'm fair, you can't come argue that I'm not discriminating against anyone. But it does this knowing that it just made it not cost effective for anyone else to apply. Okay. Once we have, let's skip this. Okay. Results. Let me choose what to talk about. No, I will talk about this. Okay. So once we understand these relations between what happens to the firm and what happens to the candidate, then we get this very nice. We get into this very nice state when we can talk about what something called a social planner does. A social planner is this imaginary entity in economics. Think about it as the regulator or the government, which his interest is the well-being of society. Okay? So such a social planner is probably not going to be happy about the fact that only one group applies. Right? Maybe it wants to somehow encourage the firm to learn a classifier under which more groups apply, or everyone applies, or certain groups apply. And what we get is that it's possible to do this with subsidies. Okay, so the problem we had before is that the learner could make different groups apply by controlling their individualized threshold. But it can do this only if it knows what the groups are. So it looks at users, you're group 5, you're group 6, I'll apply this threshold, that threshold. It seems natural that if we were to restrict the firm from not being able to know who is from what group, then that power should somehow go away. It can't fully determine applications. So the idea here is to enforce this independence, make prediction be completely independent of the group. And for those of you familiar with the fairness literature, this is known as statistical parity. But our use here of statistical parity is different. What we get now is that in a strategic learning objective, if you add these independence constraints, then we again get this ordering phenomenon, that applications have to follow a certain ordering. But that ordering is not the score function, it's the base rates. So this is something coming from the population itself. So in a world where someone, either the firm or the government, has the power to enforce these constraints, make sure that the classifier doesn't know what groups people belong to, then the classifier has power in determining who applies, but it has to follow the order of base rates. Okay? And why that is good, it's because we can introduce subsidies. If I give a certain group a certain amount of money by reducing its costs, then I can bump group up in this order because it affects only the base rate. Okay. We have results. We'll have to skip because I want to talk about the summary. Okay, so I talked about the fact that when we learn in a setting where we have to acknowledge that they have agency. I talked about a particular problem where that agency comes in the form of self-selection, that is people deciding whether to participate or not. It has an immense effect, a potential effect on learning outcomes. There's something to do about it, but we have to be careful because once we anticipate this behavior, learning gets all this extra power that maybe shouldn't have. There's also something to do about that if you have a way to regulate. There are a lot of interesting future questions. Most of them have to do with the assumptions that we made, but also additional questions. I'd like to go back to the original motivation. Remember, just started out with the big failure of Amazon in their screening. Now I crossed out the important part, which is the reason it failed was that it was easy to show that it was very biased against women. Okay, so the screening process itself had this inherent bias that it didn't. Women were very less prone to pass screening than men. Okay, this was a big, created a lot of noise, and everyone sort of blamed the data. The data was biased, and so learning just took the bias from the data, did nothing about it, and then you got this bias. Okay? And this led to a whole lot of discussion in a huge literature about how to learn unbiased classifiers from biased data. What we think of our project is doing is answering the question, but why was data biased to begin with? Why did the data have, say, less women than men? And one possible answer is, well, self-selection, right? Because there was some previous criteria which made it less cost-effective for women to apply. And so the data included less women. But then you can ask the sort of questions, well, why was self-selection that way? And it's impossible to think about these without taking into account time. So we have this new project that talks about self-selection over time. What's nice about it is that we think about it as an evolutionary dynamic process, okay? And we think about regulation as conservation. Maybe one day Eden, my student, will come and talk to you about it because it's a very fun project. We also have another project about competition. So this was about there's one firm and the choice is whether to apply or not. But there are many firms in the world, and once there are, say, more than one, then they compete over contestants and cool stuff happens. Okay. I'll just end with this. If anyone is going to ICML, Rich Guy, I'm giving a tutorial on strategic learning. I invite you all to join. Thank you.